In today's lab, you will measure the latent heat of liquid nitrogen. You will lower an aluminum cylinder at room temperature into liquid nitrogen and measure the mass of liquid nitrogen that is vaporized in order to cool the cylinder. You will also use the same procedure to measure the specific heat of another substance. Temperature is a measurement of the average kinetic energy of the molecules in a substance. In a solid, this energy may be in the form of vibrations. As heat is transferred to this substance, its temperature, and therefore its molecule's energy, increases. The amount of heat needed to change the temperature of a substance by some amount is proportional to its specific heat. The specific heat varies for different substances. Heat is positive when a substance absorbs heat and increases in temperature, and negative when it releases heat and decreases in temperature. The absorption and release of heat can also cause phase changes. Changing from a solid to a liquid or a liquid to a gas requires an input of heat. The amount of heat required is proportional to the mass of the substance being vaporized times the latent heat of that substance. Vaporizing more mass or vaporizing a substance with a higher latent heat will require more heat. To condense a substance from a gas to a liquid, the same amount of heat is released. We will assume that all of the heat from the aluminum cylinder as it cools down goes towards boiling off liquid nitrogen. Therefore, the heat or energy in the system is conserved. By measuring the amount of mass of liquid nitrogen evaporated and the change in temperature and mass of the aluminum cylinder, you can calculate the latent heat of vaporization for the nitrogen. To perform this experiment, you will use a stainless steel canister to hold the nitrogen, a dual pan balance to measure its mass, an aluminum cylinder, and assorted weights. You will also use a stopwatch and a thermometer. First, zero the balance by turning the dial until the needle is centered at 0 when there are no masses on the pans. If we place a 20-gram mass on the left pan, we can rebalance the scale by moving the slider over to 20 grams. We can also balance the scale by adding a 20-gram mass to the right pan. You will use this scale to measure the mass of the liquid nitrogen before and after the cylinder has been cooled. The aluminum cylinders will be stored in a water bath between labs so as to allow them to thermalize more quickly to room temperature. Measure the initial temperature of the aluminum cylinder using a fluke thermometer and record this value. Place the canister with the liquid nitrogen and the aluminum cylinder on the left pan. Add weights to the right pan and adjust the sliding masses until the scale is balanced. Record the mass required to balance the scale just before dropping the cylinder into the nitrogen. Lower the cylinder into the nitrogen and start the timer. As the nitrogen boils off, the mass on the left pan will get lighter and the needle will move towards the weights. When the nitrogen stops boiling, stop the timer and immediately balance the scale and record the mass. The mass of nitrogen that has evaporated will just be the difference between your two measurements. Before calculating the latent heat of the liquid nitrogen, you need to correct your measurement for the amount of mass that evaporated. Without the cylinder, some of the nitrogen will still boil off due to the heat of its surroundings. Use the timer and the scale to measure the background rate of the liquid nitrogen evaporation without the cylinder. How much nitrogen evaporated due to this background rate while the cylinder was being cooled? The heat lost by the aluminum is equal to its mass times its specific heat times its change in temperature, while the heat gained by the liquid nitrogen is equal to the mass evaporated times the latent heat of vaporization. Use the above equation we derived previously and your corrected measurement of the mass of the liquid nitrogen that evaporated to calculate the latent heat of vaporization of the liquid nitrogen. Choose some other object you would like to freeze and determine its specific heat using the same procedure. Be sure to use the actual value for the latent heat of liquid nitrogen rather than your calculated value for this measurement. Look at a table of specific heats. Can you guess your object's composition based on its specific heat?